I'm going to explain this in more than one way and more than one time, okay? Because kids truly don't sort of get all the pieces, okay? Okay, guys back, you're going to have to listen, okay? You're going to have to stop the conversations. I'm going to have to move. If you don't want that, stop talking, listen. Okay, so Robert Millikan. It was performed in 1909. This is the same handout that I just handed you, am I right? Yeah. Excellent. Okay. So this was 1909, quite a few years ago, over 100 years ago. I think at the University of Chicago, if I'm not mistaken, because I've read it 1,000 times. He determined the size of the charge on electron. Highlight that for me, because that was the purpose. He wanted to know what is the charge, how much electric charge is there on a single electron. How big is an electron? Pretty small. Anybody know what the mass of an electron is? Nobody knows. I don't even think I know. I know a lot of useless information. Way too much. Mass of an electron. 9.1 times 10 to the minus 31 kilograms. So 0.000000000. How many zeros? Well, actually 30, right? 91. Right? Because the right? 30 zeros, 9 kilograms. Pretty darn small. Okay. And what is the charge on an electron? -1. Is that all? We're going to come up with -1 here? No. We're going to get it in coulombs. Okay? We're going to get it in coulombs. Okay, so he also determined that there was a smallest unit charge, or that charge is quantized. In other words, that's the small, you can't cut it down anymore. That's the smallest value that it comes in. Okay? It's kind of like, and I know people always argue, it's kind of like eggs. Right? You can buy a dozen eggs. You can't really buy a single egg. Maybe it'll convert. That's always bad. Give me something else that you can't make less of. You can't slice it up. You can't make it smaller. Pants. You can buy a pair of pants. Can you buy half a pair of pants? You could. See, I can never come up with quite the good one. Quantized means that there's the smallest possible value. You can't get any smaller. Okay? He actually received the Nobel Prize for his work. We're going to explain that experiment here and show how Millikan was able to determine the size of a charge on a single electron. So I'm going to explain how he did it. Okay. So what he did was he put a charge on a tiny drop of oil and measure how strong an applied electric field had to be in order to stop the oil drop from falling. What? He put a charge on a tiny drop of oil and measured how strong the applied electric field had to be in order to stop it from falling, to actually suspend it in air, to have it hover in air. He was able to work out the mass of the oil drop, and he could calculate the force of gravity on one drop. He could then determine that the electric charge that the drop must have. By varying the charge on the different drops, he noticed that the charge was always a multiple. What does the word multiple mean? What are the multiples of 3? 1. No, that's not a multiple of 3. 3, 6, 9, 12, 15, right? Those are the multiples of 3. He's saying that the charge is always a multiple of minus 1.6 times 10 to the minus 19. That's a number you're going to have to know. That is the charge on a single electron. 1.6 times 10 to the minus 19 coulombs. 0.000000018 Okay? So, he found out that, let's just talk about this multiple thing here. By the way, the word multiple is a key word that I look for on the test explanation, because I want kids to know that he's dealing in multiples. Okay, so let's say that he came up with these charges. Let's say he came up with a charge of 12, 15, 9, 6, 3, 9, 15, 18, and so on. Those are all multiples of 3. Okay? So what he likely did was he likely graphed these and probably found a straight line. And when you found the slope of that line, what would you get? You'd get 3. The slope of it would be 3. Okay, but he didn't find it to be 3. This is what happened. He got charges of 3.2 times 10 to the minus 19, 4.8 times 10 to the minus 19, 6.0 times 10 to the minus 19, 1.6 times 10 to the minus 19. Those are all multiples of 1.6 times 10 to the minus 19. And when he graphed them, he would have found a slope, and the value of the slope would have been about 1.6 times 10 to the minus 19. What year did he do this? 1909. Did he have his MacBook out to graph it? No. Did he have his Android phone out to graph it? No. He did it on graph paper. It's pretty impressive. It's along the lines in my books of Galileo. Remember when you guys were all impressed how he got so close? Right? He did this all with pencil and paper. Do you think he did it in one period? An hour period? Oh, probably not. I believe it took him about a year and a half. Okay? Okay, so here's how it worked. This is the apparatus here, okay? Now, I actually have an apparatus I'm going to show you right away. Okay, but here's the picture of it. So he's got what's called an atomizer. It's a fancy word for a spray bottle. So he has this spray bottle full of oil, and at the top, he's spraying these oil droplets into this upper chamber. There's 2 chambers. There's the upper chamber, upper compartment, lower compartment. And he throws them in there, sprays them in there, and there's a hole. Can you see this hole right here? Some of the oil droplets get sprayed in and fall into this hole. Okay? And they will continue to fall down. Now, these oil droplets are really, really, really tiny, and they're really, really sort of light. When really light things fall, what do? Oh, really slow. Okay, now these things are way smaller and way lighter than this Kleenex. Okay? So they're going to take a long time to fall. Now, he was able to hook up a microscope right here, and he could watch them fall. And they would fall with, what's it called when a thing doesn't accelerate as it falls? Constant speed or terminal velocity, right? And he could actually figure out how fast they are falling. He would have had a stopwatch, an analog stopwatch, and he would have had little marks over here, right, that could help him to figure out how fast it's actually falling. Okay? And I think this is all on the next page here. Yeah, here it is here. An atomizer spray to fine mist. You guys should find the spot there. Underneath, I think, right? Atomizer spray to fine mist of oil droplets into the chamber. Some of these tiny droplets fell through a hole. Millikan first let them fall until they reached terminal velocity. Using the microscope, he measured their terminal velocity, and by use of a formula, calculated the mass of each oil droplet. Okay, now we're going to sort of simulate that in a different way. I'll explain that in a bit. He used like things with viscosity. It was kind of a complicated computation, but basically it boils down to he came up with the mass of each oil droplet. Now, how big would that mass be?
Not very big.
Not very big. Oil is light. Doesn't have a lot of weight to it. Next, Millikan applied a charge to the falling drops by illuminating the bottom chamber with X-rays. This caused the air to become ionized. You guys remember from chemistry, what's an ion? Uh-oh. What's an ion? You've got to watch out for them. A charged particle, right? A charged atom, really. Yeah. Okay? So it became ionized. So there's charges in here. He applied this X-ray, right? This caused the air to become ionized and the electrons to attach themselves to oil droplets. So in other words, he made the oil droplets charged. Some accounts say that just because of the plastic tubing in the atomizer that the oil droplets were already charged. I think from my research it tells me that he thought that would work. It sort of worked. He had to do the X-ray thing to make it better. Doesn't matter. By attaching a battery to the plates above and below this bottom chamber, he was able to apply an electric voltage. So this is a battery right here. This is the symbol for battery. And so there is a charge on this plate, okay? So one might be positive and one might be negative, which would create what inside there? You've got two charged plates. It's going to create this whole unit. It's going to create the electric field. Okay? So he's generating an electric field in here, and he's putting these oil droplets in here. There's more to it. By the way, I'm going to have to repeat myself. Do you get the feeling that you're going to have to get this explained more than once? Yeah, that's why I went to the research project, because you have to think about it and research it, come it all together, and then I would re-explain. It worked pretty well, but anyways. By attaching a battery to the plates above and below this bottom chamber, he was able to apply an electric voltage. The electric field produced in the bottom chamber by this voltage would act on the charged oil droplets. If the voltage was just right, the electromagnetic force would just balance the force of gravity on the drop, and the drop would hang suspended in mid-air. Here's the picture that you should draw right beside that paragraph. Here's a close-up of the oil droplet. It's in the Earth's field, and so it would be experiencing a weight force due to gravity, Fw. Right? And when he turns on the electric field, there's going to be a force up if he plays his cards right, and that is the Fe. And if he adjusts that electric field just right, he can make those two forces equal. And the drop will do what, Jason? Be suspended in midair because the forces are equal or balanced. Okay, make sense, Lane? Okay, so he has the mass. Fw is equal to mg. Okay, he has the mass. He knows gravity. He can figure out weight force. And once he gets those forces balanced, then that Fw is equal to Fe. Now remember yesterday, we dealt with E equals F over Q, and I didn't give you much time to work with it. But with that, this Fe is this guy here, right here, right? He knows what electric field strength he's creating with his battery, so he knows this one. He knows the Fe. How come? Because it's equal to the Fw, and from that, he can solve for the charge, which is Q. He can solve for the charge on that little teeny tiny oil droplet. It is pretty smart. And then he did it many times, Jason. And he got all the charges were always a multiple of that number, 1.6 times 10 to the minus 17. There's a lot of parts in here, right? There's a lot of pieces at play here. I'm going to have to re-explain. I get it. Okay, I'm sort of giving you the... Well, I was going to give you the summary to begin with, but I've kind of gone a little bit more in depth than I planned. Okay. It says now you try it. Click here to open a simulation. Not working on your paper, right? I'll show you one. Okay. First, allow the drops to fall. Notice how they accelerate first due to gravity. Quickly, air resistance causes them to reach terminal velocity. Now focus on a single falling drop. Adjust the electric field upward until the drop remains suspended in midair. At that instant, for that drop, the electric force on it equals exactly the force of gravity on it. Some drops have more electrons than others, so require a higher voltage drop. So what you would see when you click on that simulation, you'd see a bunch of oil droplets. Some would be falling, some would be rising, and there'd be one. He'd have to pick one and highlight it. That would be the one that would just suspend. And he'd focus on that one. And then he would do another one. He'd painstakingly do this over and over and over again. He should get a life, right? He really wanted to know what the charge on a single electron was. What was the reward at the end of all this? He got a Nobel Prize. Plus, physics teachers across the globe talk about him too. Okay. What's that? It's not, the big deal is not oil droplet, the big deal is he found out the charge on a single electron. It's a fundamental constant in nature. Okay? It's an important thing. It's an important scientific discovery. Okay? Now, I've explained this already, but I'm going to do it again. Okay, let's look at the calculation that Millikan was now able to do. When a drop is suspended, its weight mg is exactly equal to the electric force applied Q times E, right? So, where does this Q times E come from? Well, if you go E is equal to F over Q, right? If we solve that for F would equal, Q times E. So you've got the QE is equal to the mg. Right? The value of E, the applied electric field, m, the mass of the drop, and g, the acceleration due to gravity, are all known values. So you can solve for Q, the charge on the drop. Millikan determined the charge on a drop. Then he redid the experiment many times. Each time varying the strength of the X-rays ionizing the air so that a different number of electrons would jump onto the oil molecules each time. He obtained multiple or various values for Q. The charge on Q on a drop was always a multiple of 1.6 times 10 to the minus 19, which is the charge on a single electron. This was the number. This number was the one that Millikan was looking for, and it also showed that the value was quantized. The smallest unit of charge was this amount. It was the charge on a single electron. He couldn't find a smaller value, which meant that that was one electron. You couldn't get any less. Okay? Now, some interesting soap opera drama that's not on the page. Okay? It's part of the research project. It's kind of interesting. Millikan was a bit of a jerk. Okay? He had a grad student. His name was, I can't remember. I kind of don't remember that. I read it 100 times. He basically had his grad student do most of the work, and then he took all of the credit for it. He was a bit of a jerk. Deal was, Millikan allowed the grad student to do some stuff, and then the grad student sort of got some credit. It was kind of like a deal they kind of had. Millikan came way out ahead, and, smelling like roses kind of thing, right? He came way out ahead. He was the professor. The grad student did all the grunt work. Millikan got all the credit. Okay? Hopefully no one in this room is related to Robert Miller. I just called him a jerk. Anyone? Not that you know. Okay? So that was one controversy as part of it, right? The second controversy was this. Millikan ignored results that he didn't like. Remember the other day when we were doing that lab with gravity? And there was a few of you that came up with values, right? You had your slope, and there was a few people that were like, here, your gravity's like this. But then there was like one that was kind of like way out of whack. And it was causing you didn't get 9.8. Remember that? And I said, what did I say? Well, that one kind of looks out of whack. Let's try that one again. And what did you do? Well, you tried it again, and you probably got something a little bit closer, and you got a little bit value, a little closer to 9.8, and you felt good about yourself, didn't you? That's not the way you're supposed to do science. It was kind of interesting how I started doing that, and I realized, oh yeah, this is exactly what Millikan was doing. I'm going to let the kids do that. Right? You were doing it the wrong way. Now, having said that, we know the value we should have got was what? 9.8. Right? We know it's been proven a gazillion times. We know it's agreed upon. Scientists across the globe say it's 9.8, and we know that's what it is. And so we were wondering why our results didn't show that. We were doing an experiment to basically verify, to prove it's 9.8. And were there some mistakes made? Did you guys make mistakes when you did that lab? Of course you did. In fact, I don't remember who I was talking about, but I think what happens is this. What was you going, right? I think what happens is this. You put your finger on the button. You release the ball. I don't know how to do it. You release the ball, but you don't release your finger at exactly the same time. Right? It's close, but I don't think it's perfect. And so I think what happens is you're hanging on to the ball just a little bit longer than you need to, which is why those results aren't perfect. Still way better than we used to get. Okay, so what does this have to do with Millikan? Well, every once in a while he would get a drop that didn't fit the data. And so he would just say, screw that one, I was wrong, I'm not going to deal with it, right? He was throwing out data. Now the problem was, the number 1.6 times 10 to the minus 19, scientists didn't agree on it. He was trying to find it. Is that a valid thing to do in the name of science? Can you just throw that out and say, it's not going to count, that one doesn't count. I don't like it. Is that okay? We can do what he wants. Is it ethical, maybe? From a scientific standpoint. No one got hurt by it, but is it the right thing to do? And there's controversy, right? Most people will say, now we're shaking our head, most people say, yeah, you shouldn't have done that, right? I think I'm somewhere in between. If you've got an outlier, if you've got a number that doesn't make sense, a red dot that's way out, the trend is this. I think you should go looking for, why is that one wrong? Maybe you are holding the button and letting them all go at the same time. Maybe you're doing something wrong that day. Maybe the temperature went up in the lab that day. Maybe the air pressure went up. Maybe he didn't have his morning coffee. I don't know. Maybe the grad student was out partying with his buddies. Maybe there's a reason for it. Okay? So you can't just throw it out because, well, I don't like it. But if you can come up with a reason why maybe we should throw it out, maybe that's okay. Does that make sense? Okay? Okay. I need to gather my thoughts here. See, because this is not the way that I normally do things. I got one more handout here for you. Does the overall sort of general gist of the experiment make sense? If you had to summarize it into sort of key points, what would those be? Should we do that as a group? You know, we could do this as a group activity. That might work here. I'm winging it here. Let's do that. Get a partner, group of 3, get a sheet of loose leaf, and I want you to write down, let's say, the main 8 points from that explanation. Can you do that, you think? Give it a whirl and we'll compile it together. I'm winging it here. This is something new for you. Find a partner, find a group of 3, get a sheet of loose leaf. I want the 8 main points. This isn't going to be entirely boring. I do have one funny video to show you at the end. I want 8 main points. Okay, is that enough time? Now, we're going to try to come up with 8 main points, and then we'll put them sort of like in the right order that makes, an actual paragraph that makes sense kind of thing, and not just sort of like random word salad kind of stuff. Zoe, give me one of your first main point. Calculated the mass of the drop. And you said the terminal velocity? You could combine that, right? Using terminal velocity. Using terminal velocity calculates the mass of the drop. Okay, let me just spell it right. Okay. Oh, terminal velocity. You guys don't have to write any of this down. Then we're going to put it in the right order at the end. Okay? You guys are there, Elaine?
It is always natural of negative 1.6.
Found that the charge was always a multiple of 1.6 times 10 to the minus 19. Oh, 19. Yes, you paid attention when I said that was a word that I would be looking for. Okay? Another group back there. Anna, what do you guys got? Anyone, doesn't matter. Right. If the what was just right? If the what was just right, not the charge. Well, actually, it's the charge and the electric field strength. If the electric field strength was just right, the drop would suspend in air. Okay? Nolan? Created an electric field between the 2 plates. Okay? Ladies at the front here, Tia?
Based off of one drop boilers based off of.
Did it many times. Ah. Jason? What's the next one? Eh? Oh, you were back there. Oh, it doesn't matter. Oh, it's back there. Sarah? What do you got there? There's Anna. The purpose, right? Purpose was to find the charge on a single electron. Is that what you're saying, Sarah? Okay. Gerardo? What do you got? Did you guys come up with something? I know it's tough. English, Spanish, German, it's tough. Yeah, I get it. It was this, right? That kind of goes with this one, right? This was the smallest multiple. It was the smallest charge found. I'm gonna do that. I'm gonna stick those together, okay? Vinny, what do you guys got?
They illuminated the bottom chamber with X-rays.
Okay.
Make the air ionized.
Oh, that's a lot of words, man. How about, can we say charged the drops by applying an X-ray? Does that simplify that a bit? Okay. Okay, so if you had to put this in order of a paragraph, obviously these aren't sentences, but if you had to put these thoughts in order, if you were explaining to someone, which one would be first? Probably the purpose, right? Would be number one. What would be the last one? Like the result. Probably these two, right? Okay, so we've got our bookends there. Those are first and last. Okay, now what's next? If you're creating a paragraph here. His purpose was to find the charge on a single electron. How did he do it? This one? Okay, create an electric field between two plates. Charge the drops. Okay. Then this one. Okay. Then what? Probably that one. And then that one and that one. Okay, I'm not going to disagree with that. I'll give you a few seconds to read that over, and then I'm going to ask you, are there parts missing, Zoe? It kind of feels like it, doesn't it, right? How many points we got there? 1, 2, 3, 4, 5, 6, 7. And are there points missing? I would say so. Megan, what would be something that we missed along the way here? I think everyone agrees the purpose is good. What else? Would a diagram help? Like if I went back and I was explaining this on a test situation and I drew this, would that be helpful? Remember, really, what's the goal here is for you to convince me that you know what you're talking about. That's what your goal is. You're trying to convince me that I get this experiment. Would drawing a diagram be part of that? Bingo. Okay, so now we got a diagram. Now I haven't really said anything about what? I haven't really said about how the oil droplets got there, did I? Right? So you probably should say, create an electric field between two plates, but there's this upper chamber, right? We should probably say something like, sprayed oil droplets into the upper chamber. We probably need to say that, right? Just to sort of give some background. Sprayed oil droplets into the upper chamber. Create a electric field between the two plates. Maybe we'll say in the lower chamber. Does that make sense? We're kind of like doing like a rough draft here, are we not? Okay, create an electric field between the plates in the lower chamber. Charge the drops by applying an X-ray. That's good. Using terminal velocity, calculates the mass of the drop. If the electric field strength was just right, the drop is suspended in air. Okay, now, yeah, that's true. But it feels to me like there's something missing in here. This is all good. Does it feel like there's something missing in here? What do we need to talk about in there? The drop was suspended in air. Weight force. Do we need to say anything about like that? Should we include that diagram? Probably. What would you say about this? If the electric field strength was just right, the drop would suspend in air. The weight force and the electric force are now equal, right? And how do I get from the electric force to the charge? Don't I have to? He could then solve for the charge on electron, charge on the oil droplet, charge on the droplet. Let's go through this step by step. I'll give you time to write this down. Okay? Oh, we got lots of time. I'll give you time. I want you to think. Purpose was to find the charge on a single electron. He sprayed oil droplets into the upper chamber. Does that kind of go with the diagram? Do those kind of things kind of go together? Kind of. Create an electric field between the two plates. You're kind of describing what it looks like. Create an electric field between the two plates. That kind of goes with the diagram. Charge the drops by applying an X-ray. Using terminal velocity calculates the mass of the drop. If the electric field strength was just right, the droplet is suspended in air. The weight force and the electric force are now equal. He could then solve for the charge in the droplet. He did it many times, and he found that the charge was always a multiple of 1.6 times 10 to the minus 17, and that was the smallest charge found. Do you feel like we've covered all the bases? I do. I'm pretty good with that. How many points is that? Guess it's more than 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's almost 10. Plus your diagrams. Would you like me to leave that up there? I can post them to Schoology, of course. I'm going to put them a little bit closer together so that it all fits on one page.